Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have John Banovetz with us today. Hey, John.
Hey, pleasure to be here. Thanks for having me.
Well, thank you so much for agreeing to talk about your lovely article. What's your geolocation? Where are you at?
I am at my office at Purdue right now, West Lafayette, Indiana.
Okay. And where are you at in your trajectory?
I am on my final year. Hopefully, well, fingers crossed, hopefully by this point next year, I'll have my PhD.
Awesome. I look forward to calling you Dr. John. That will be fantastic.
Yeah.
That's great. So it's Memorial Day here in the US, May 31st. I'm in Phoenix, Arizona. We haven't quite hit the power switch yet. So we'll only get up to 35C or so, 36C. But in another week or two, we'll power up into the low 40Cs. How about in Purdue? Is summer there yet?
It kind of came for a little bit. It was getting up to 80 degrees Fahrenheit, but this last week it's been like down to 60. And then by the end of this week, it's supposed to come back up again.
Okay. Are the trees doing their thing? Are the trees blooming?
Yep. Yeah. Trees are blooming. I started my little herb garden in the backyard. That's going well. So
very good. What are you growing?
I got 2 different types of basil, sage, thyme, cilantro, parsley, mint, and dill.
I'm coming over to your house for dinner. That will be awesome. Very good. Congratulations on that. I have a lemon tree.
Oh.
Lemon tree, and I have some citrus trees. And they'll come later. But yeah, they're going. So it'll be very cool. So maybe we can swap some herbs for some or something like that. So,
I will be down with that.
Very cool. John, what do you like to do for research?
I do a little bit with diffuse interstellar bands, but primarily my research is on supernova remnants, especially oxygen-rich supernova remnants, and determining their center of expansion and age.
Cool. That's a pretty awesome poster over your head there. That looks like maybe a AAS poster.
This was actually for, I believe, the Midwest workshop on transients. I might have the name slightly off, but
put the link in the video below on the right one.
Yeah.
Cool. And that is going to bring us to this very lovely APJ article, The Center of Expansion and Age of the Oxygen-Rich Supernova Remnant 1E0102.2-1719. And John, take us away.
Yeah, so in this article, we're just trying to determine the center of expansion and age of that oxygen-rich supernova remnant. I'm just going to call it E0102. Instead of doing the whole big name.
One telephone number, yes.
Yes. So yeah, this is especially important. We need these numbers to try and kind of understand supernovae. So it's one of the motivations behind this research is to get these 2 kind of fundamental properties of a supernova remnant so that there can be like constraints on supernova simulations. And so there's a few cool papers that I can reference that actually use some of the constraints in their simulations. But yeah, this work is just on E0102. E0102 is the supernova remnant in the Small Magellanic Cloud, and it's one of the few oxygen-rich supernova remnants that we can measure the proper motions of their ejecta, the ejecta knots of the original supernova. Yeah, there's progenitor mass ranges from like 25 to 50 solar masses for what caused the supernova that created this remnant. Most importantly is there have been previous age estimates. The problem is the early age estimates put it around 1,000 years, and later age estimates put it around 2,000 years. So kind of a big discrepancy there.
Indeed.
And so Yeah, that's one of, we want to try and narrow that down. There was also a previous proper motion study done of EO102.
Okay.
They found a center of expansion. Again, we want to narrow that down because recently there was a paper that came out that proposed a neutron star candidate for EO102.
Ooh.
Yeah, and one of the things that they had in that paper was the initial kick velocity. So the supernova goes off, the neutron star, the remnant can kick off with a certain velocity, and you use the age and center of expansion to determine that kick velocity. That's one way of doing it. And so they found it to be using the old age estimate and center of expansion to be about 850 kilometers per second. We want to really hammer down those two values.
Mm-hmm.
And so if you can scroll to figure 1.
Figure 1, and let's blow these up. People can see them. I'll go left, right.
Yeah, so there's just a very pretty image of EO102 on the left, just taking a different filters. So there's red, green, and blue for ejecta moving away from us in the plane of the sky and towards us respectively. Just a nice, pretty picture of EO102. The image on the right is kind of what the data actually looks like when you load it up into DS9.
Mm-hmm.
This is one of the images we used. There were 4 images that we looked at, one taken in 1995, one in 2003, one in 2013, and one in 2014. I'll touch on those a little bit. I'll touch on those later. This is one from 2003. The red circles, all they indicate is stars that we use to align the images.
Got it. Yep.
And so with those 4 images, what we did is we wanted to measure the proper motion of the ejecta in order to find that center of expansion and age. We created 3 baselines. The first one was between 1995 and 2014. That one was just longest baseline. We should see the largest shift and the proper motions and get a more accurate kind of answer and result.
Cool.
And then there was another one, 2003 to 13. That one leveraged the fact that we were actually able to use the same instrument and filter between the 2 images. So 1995 was with PIC2 and the F502N filter, and 2014 was WFC3 and the 502N filter. And that was actually, turns out was a big deal. And then just briefly, the third one, the third data set that we created was trying to use all the images and find the proper motions with all the images. What we ended up doing is just using the 2003 and 13 data set. We found that slight difference in filter, which actually, if you want, you can jump all the way down to the appendix.
Sure, absolutely. Give me 1 sec. Down to the appendix and boom.
So yeah, while it was the same filter, that F502N, very different band passes between the 2 instruments. And so you can see that mostly in the right image.
Yeah.
And so what ended up happening was you would blink between the 2 images to try and find the proper motion. And you have a little tiny knot that would suddenly explode.
Yeah.
With light, because we get all that extra light, and that change in luminosity caused a lot of ambiguity in where exactly that center was. Were we tracking the same position in both images? And so we decided to just do the 2003 and 13 image because same instrument, same filter.
Nice.
You could track much more confidently between the 2 images. And then I have an example of our tracking in figure 2. Sorry, I might have you jump around.
That's okay. Jumping around is perfectly fine. Figure 2. Okay, let's keep both these up.
Yep. And so that's just the 2003 and 13 image, kind of trying to pseudo blink between them so you can see the movement of the knots. And you can see that they are going away from that center of expansion that we calculate. That's what the red arrow shows. And yeah, so we did this for 96 knots in the 2003 and 13 images. And what we found is that there is actually an asymmetry in the proper motions of the knots in respect to position angle. So you'd scroll down to figure 5, that shows that the best. So yeah, well, you just scroll down. Figure 3 just shows all the vectors with all the data sets, but figure 5 is kind of a good money shot, so to say. So this figure is kind of doing a sweep of the remnant and determining the proper motion in 20-degree slices. And so the blue dots are the proper motions. The blue lines is kind of the spread in proper motions within that slice.
Okay.
The red horizontal line that goes across is the global average proper motion. It's about 8 milliarc seconds per year. Okay. And the orange dots is what the proper motion should be, taking the average distance away from the center of expansion of that slice, assuming that it's expanding homologously. That should be the proper motion. And you see that they're around like that 100 to 200 mark. Everything is going slower than what the predicted value should be, and around like 220 to 280, everything's going faster.
Yep.
And so you see, this kind of shows that on the eastern side of the remnant, the ejecta is moving slower than compared to the west. And so I think that if you could go to, I think, figure 9 and 10.
Sure. Interesting. Okay.
We have an explanation of where this asymmetry comes from. So yeah. So yeah, that would be perfect. So just briefly, once we found the asymmetry, picking ideal knots that might not have been decelerated was kind of the path to go. And so from that 96 knots, we picked out 45 of like the best ones. And that's what you see in the top figure is the 45 knots and their trajectories going towards the center of expansion, which is in yellow. I'll talk about how we calculated that later. And on the right is what would happen if we forced all those knots to originate from the center of expansion.
Okay.
The dashed line is taking that 8 milliarc second global average, pushing it out, I think, to about 2,500 years.
Okay.
And you see that while it fits the eastern part fairly well, the whole western part is not fit at all. And so that's kind of a big red flag that there's asymmetry somewhere. Now that, sorry.
Indeed, yes, very nice.
And so there's two causes that for the asymmetry. One could just be an intrinsic explosion asymmetry. So as the supernova exploded, some ejecta went off faster than others. One of the other cases is an inhomogeneous surrounding circumstellar material environment.
Okay.
And so that's what we prefer in this paper. And you can kind of see it in the bottom figure. So the bottom figure shows integrated iron-14 emission.
Yep.
So this is taken from Voigt et al. 2017. And you see in the eastern part and kind of the northwestern part, there's more emission. That's indicative of the forward shock running into the CSM. And you can see on the right now with all the knots that all the slower, the red knots are all on the eastern side.
Yeah.
And so we believe that this inhomogeneous expansion is caused by a non-uniform circumstellar medium environment.
Mm-hmm. Very cool.
And
what are the green dots on the right?
the green dots indicate the faster knots. And
okay.
I'd say keep those in mind. Those are what we use for the age expansion, which I'll get into now. So just if you want to scroll up, I think figure 5.
Figure 5.
Or sorry, figure 6.
Figure 6.
We already saw figure 5.
Okay, all good.
Yeah, so actually, if you could scroll a page up, there's an equation that we use. Yeah, that one.
Likelihood function, yeah.
Yep. And so knowing that there was this asymmetry, we it kind of limited how we would calculate the center of expansion, because there's a few ways in the literature before would assume a homologous expansion.
Sure.
And then find the center of expansion that way. We couldn't do that. So we used this likelihood function. It was used previously in a paper by Thorstensen et al. 2001. Essentially, what it does is it finds the point that has the smallest distance between it and all the other trajectories.
Yes.
And so that's how we calculate the center of expansion. We want to use this one because we didn't want to be dependent on the proper motions of the knots, since we knew that some of them might have been decelerated. We just wanted to know about the direction. And so that's how we calculate the center of expansion. And then for the age, all we do is find out how long it would have taken a knot to get from our calculated expansion to where it is today. And so just distance divided by proper motion. And for that one, because again, we knew that there was an asymmetry in the proper motions, what we did is we just took the fastest 22 knots, with the idea being that the fastest knots should be decelerated the least, so a true representation of their initial proper motion.
Okay.
And so if you scroll down to figure 6, that shows kind of the difference. So the left side shows what would happen if we actually just used all 96 knots.
Okay.
And you see that the age is about 2,000 years, and it's fairly close to kind of the last age estimate of 2,050 years. So if we just used all the knots, we would have gotten a similar answer to that. However, just choosing the fastest knots, we find that it's about 1,740 years, 1,740 years. And so these are the fastest 22 of the 45 knots that we used. And then as kind of a sanity check, what we also did is we took the knots that had the fastest proper motion, the ones that were furthest away, and kind of in the southwest portion, so there shouldn't have been too much interaction compared to the eastern side. And actually, if you scroll up to figure 3, I can just point out the region that I'm talking about. So just briefly explaining figure 3, the left side is all 3 of those data sets that I mentioned earlier, and all the vectors. The right side is the one I want to focus on. Those are our 45 kind of unique, or not unique, but
gold.
The gold set,
the gold
so
ones.
to say. Yeah. So you see on the right side, there's kind of that like bow.
Yeah.
That's the, we tested it with those vectors because those showed to have the highest proper motions, especially those to like the lower right of the bow. And using even this like subset of a subset, we were able to get around 1,740 years. So it's kind of a nice sanity check of our age. And so if you scroll down to figure 7, that'll show our center of expansion as compared to other results.
Okay. All right.
Yeah. And so our center of expansions in the yellow there, we had an error radius of about 1.77 arc seconds. The previous center of expansion is the red cross with the dotted lines, and the X's show different kind of center of expansions if you took the geometric center of the X-ray forward and reverse shock.
Okay.
And then the purple, that's the candidate neutron star that I mentioned earlier, all the way down there. And so if you use our center of expansion and our age estimate, and with that displacement, you find that this candidate neutron star would have had a kick of about 1,070 kilometers per second, which is really fast.
It's high.
Yes. Yeah. So to put in perspective, there was a study of like 200 plus pulsars, and they found the average velocity of the pulsars were about 300. And that, if you then just also compare with supernova remnants, they're about 300 to 500 usually of like known neutron stars. There are 2 exceptions. One is Puppis A. That neutron star has a kick velocity of about 750 kilometers per second, I believe. And so fairly high, especially once you start, I think the error bars would overlap. And then the other one is N49, which I think Katsuda et al. 2018 calculated a kick velocity of 1,100 kilometers per second.
Okay.
There is a caveat, I would say. There is no proper motion derived center of expansion for N49. So they use the center of the X-rays, which you can see with this figure, it doesn't always line up. And so I would say there's maybe a little asterisk with that.
Sure. That said, they're still getting 4-figure kick velocities.
Yeah.
Yep.
And so I should also say that with this candidate neutron star, since the paper came out in 2018, last year, I think there were 2 papers that came out that did a more detailed analysis of the X-ray point source that was this candidate neutron star. And right now, the true nature of this source is still unknown. The latest paper that came out said it was most likely just excited ejecta that was causing. So I should say the reason why this is this candidate neutron star is preferred is there is a ring of neon emission that surrounds this X-ray point source. For those curious, I would go into Voigt et al. 2018. It's a really nice, it's just a nice little bullseye. And so they're kind of explaining, there still needs to be an explanation of what's causing this kind of excited neon ring. And so the initial paper said it was this neutron star powering it, but the more detailed analysis, it's unsure whether it's an isolated neutron star. It could maybe be like a pulsar wind nebula or something. But again, the last paper, the conclusion was it was most likely just excited ejecta. So, which is, so yeah, I think that's everything.
Okay, very good. Very good. Yeah, very nice, nice images. So you touched on it a couple of times as you're walking through this very lovely article. And that is, where do we go from here, given your published article and given some of the current disagreements in the literature? Is there a new campaign of observations on this particular supernova remnant or on other ones? Are there calculations that could be done that would help solidify the center and the age of E102? Or
I will say so we used archival images, and so last image was 2013. Okay. And so we're coming up on that. I kind of just put in like nice 10-year marks. So we had 2003 to 13, and we're coming up to 2023. And so that could be an upcoming thing, just another epoch of data. It allows for different analyses to be made. Otherwise, I don't know personally of any maybe additional Chandra observations for the source as of yet. There could be some proposals I haven't heard about or something, but yeah, I would say up and coming would definitely, another HST observation would be awesome.
How about JWST?
I think there was a proposal, and I don't think it was accepted.
Yeah, but in general, there's possibilities of using JWST to put some more data on this particular one.
Yeah.
E102.
Yeah, I am not, to be honest, I'm not totally sure. I know that there have been a lot of Spitzer observations with dust, and I think that the dust production would be a nice thing to study. I unfortunately am more along the optical side of things.
For now.
For now, yeah.
For now, for your PhD thesis.
Yeah.
So I guess my point is there's a lot more to do on this topic.
Yes.
Narrow down some of that uncertainties. We got some new telescopes maybe we can do, and I'll give you a bright, happy few years post PhD, post Dr. John, to investigate some of that.
Yeah.
Cool. Very nice. Very nice. John, I want to thank you so much for taking the time and sharing your lovely APJ article with us.
Yeah, thanks again for having me. It was awesome.
Thank you. All right, everyone, thank you, and we will see you on the next one. Bye-bye.